Hey, welcome to The Explainer. Today, we are diving deep into a topic that can feel, well, a little intimidating: quantum physics. But here's the thing. What if it isn't some impossibly complex puzzle? What if it's just the instruction manual for our universe? In this explainer, we're going to unpack the strange, mind-bending, but absolutely essential rules that build our reality from the ground up.
So here's our roadmap. We're going to start with the biggest head-scratcher of them all. Is stuff a particle or a wave? Then we'll look at how science even talks about this stuff using the language of probability. After that, we'll get into the famous uncertainty principle, see how these bizarre rules actually build stable atoms, and then finally, see how it all clicks together in real-world tech like lasers.
All right, let's get right into it. Section 1, a particle or a wave. This is the core contradiction, the central mystery that completely baffled the sharpest minds of the 20th century.
And it all boils down to this one question: what is an electron, really? Or a photon, or any tiny piece of our world? Is it a solid little dot, like a tiny billiard ball? Or is it more like a ripple spreading out in a pond, a wave? The answer that quantum physics gives us is a completely reality-bending yes to both.
See, on one hand, you have the classical view we're all comfortable with. An electron is a particle, a dot. It's here, not there. Simple. But then quantum mechanics comes along and shows us that an electron also acts like a wave. It has a wavelength. It can do wavy things like interfere with itself, which is something a solid little ball just shouldn't be able to do.
Now, this wasn't just a wild guess somebody made. In 1924, Louis de Broglie had this incredible idea, and just 3 years later, it was proven. The Davis and Germer experiment was the smoking gun. They literally shot electrons at a crystal, and what they saw was a diffraction pattern. The electrons spread out exactly like waves. This gave birth to the principle of complementarity. Something can show you its particle side or its wave side, but never both at the very same instant. It all depends on how you ask the question.
Section 2, the language of probability. Okay, so if matter has this weird dual personality, how in the world do you describe it? The old physics rulebook just wasn't going to cut it. Science needed a whole new language.
And that new language came from the brilliant Erwin Schrödinger. He gave us the wave function. Now, this isn't your normal math equation that spits out a nice, clean answer. No, the wave function doesn't tell you where a particle is. Instead, it describes this cloud of potential, a whole field of possibilities for where you might find it.
But hang on, that's still pretty abstract, right? A field of possibilities. What does that really mean? Is the electron just kind of smeared out all over the place until you go and look for it? What's going on?
And this is where the physicist Max Born had a total stroke of genius. He figured it out. The wave function is a map of probability. Where the wave is higher, it just means there's a higher chance you'll find the particle right there if you decide to measure it. Quantum mechanics can't tell you for sure what will happen. It can only tell you what's likely to happen.
Section 3, the uncertainty principle. So if we're living in a universe governed by probabilities, well, things are about to get even stranger. This leads to one of the most famous and, frankly, bizarre consequences in all of science. This is the famous Heisenberg uncertainty principle. And what it's telling us is that there's a fundamental trade-off baked into reality itself. The more precisely you nail down a particle's position, the less you can possibly know about its momentum, its speed, and direction. And it works the other way too. Pinpoint the momentum, and its location becomes a fuzzy mess. And this isn't because our measuring tools are clumsy, it's a hard and fast rule of the universe.
So the takeaway is this: you just can't know everything about a quantum particle all at once. It's impossible, because it has that wave-like nature. If a particle has a very specific location, its wave is all bunched up, which means its momentum is spread out all over the place. And if it has a very specific momentum, its wave is long and spread out, meaning its location is anyone's guess. You can't have it both ways. This built-in fuzziness leads to something that sounds like pure science fiction: quantum tunneling. Because a particle's location is really just a wave of probability, that wave can actually, well, it can leak right through a solid barrier. It's like throwing a tennis ball at a brick wall and having a tiny but real chance that it just materializes on the other side. This isn't just a party trick. It's essential for how the sun works
and for how the transistors in your computer work. It's happening all the time.
Section 4, How Atoms Are Built. Now, you might be thinking all this is just weird philosophy, but it's not. These strange rules are the very reason that matter, the solid stuff all around us, is stable. Let's see how they actually build an atom.
So inside an atom, an electron can't just hang out wherever it wants. Its wave nature means it's forced into specific, allowed energy levels, kind of like assigned seats in a theater. We can pinpoint each electron using its unique address, which is made of 4 quantum numbers. Think of it like this. The principal number is the energy shell, like the city it lives in. The orbital number is its subshell. That's the shape of its probability cloud, kind of like its street. The magnetic number is its orientation, its house number. And finally, spin is like a personal feature. It's an internal property that's either up or down.
And now for the master rule that brings order to the chaos. Wolfgang Pauli figured this one out, and it's beautifully simple. The Pauli exclusion principle says that no 2 electrons in the same atom can have the exact same 4-part address. Every single electron needs its own unique quantum state, no exceptions.
And here's the payoff, the beautiful result of that simple rule. Because electrons are forbidden from piling into the same state, they are forced to stack up, filling higher and higher energy shells, creating structure and layers. This one principle is why the universe isn't just a lukewarm soup of particles. It's why atoms take up space, why chemistry exists, and why we have the entire beautiful periodic table of elements. It's that important.
Okay, final section. From atoms to lasers. Because once you understand the rules of the universe, you can start to manipulate them. So let's look at a perfect piece of quantum technology in action, the laser.
At its heart, a laser is a quantum machine. It all starts with pumping. You zap a material with energy to kick a bunch of its electrons up into a higher excited energy state. Then comes the quantum magic, stimulated emission. A photon with just the right energy comes along, and instead of getting absorbed, it coaxes an excited electron to fall back down. When it does, it releases a second photon that is a perfect identical clone of the first. This new photon then does the same thing, creating a cascade, an avalanche of identical photons.
And the light that comes out of this process is totally different from the light from a regular bulb. It is custom built. Because all the photons are perfect clones, the light is monochromatic. It's one single pure color. Because they all march out in perfect lockstep, the light is coherent. All the ways are perfectly aligned. And that is what allows a laser beam to be so incredibly focused and powerful. It's a direct result of us playing with the quantum energy levels in atoms.
So there you have it. From the mind-bending idea that particles are also waves to a universe built on probability and uncertainty. These strange rules aren't just curiosities, they are the very foundation of reality. They're why atoms hold together, why chemistry works, and why we can build amazing technologies like lasers. Which leaves us with one final, big question to chew on. If the bedrock of everything we know is a shimmering sea of probability, what does that really say about the solid, predictable world we think we're living in?